The topic of this video lecture is Phase II reaction. In my earlier lectures on biotransformation, we have learned that a drug undergoes chemical alteration in the body to be inactivated and to facilitate its removal from the body through the kidney. Biotransformation plays a major role in converting lipophilic drug molecule into hydrophilic drug molecule so as to enhance the elimination of the drug from the body through the kidney. Biotransformation occurs in two phases, Phase I and Phase II reactions, which occur sequentially. That is, Phase II reaction follows Phase I reaction for most of the drugs. However, there are certain exceptions. The exceptions are 1. Phase II reaction precedes Phase I reaction in case of isoniazid. So isoniazid is an antitubercular drug which undergoes acetylation, which is a Phase II reaction. This is followed by hydroxylation, which is a Phase I reaction, and the drug is finally inactivated. So in case of isoniazid, Phase II reaction precedes Phase I reaction. Second, a drug may also have an existing functional group that can be conjugated in Phase II without going through Phase I reaction. So there is absence of Phase I reaction and the drug can directly go into Phase II reaction. Example, phenol is conjugated to form a metabolite in Phase II reaction and is excreted in urine. Third, there are drugs which are highly polar in nature, for example, streptomycin, gentamicin, neostigmine. These drugs are excreted unchanged in urine without going through any of these phases. A drug may also undergo inactivation by spontaneous molecular rearrangement without an enzyme. Example, atracurium, which is a neuromuscular blocker and undergoes inactivation by spontaneous molecular rearrangement. So if we compare Phase I reaction with Phase II reactions, Phase I reaction includes catabolic reactions such as oxidation, reduction and hydrolysis. Whereas Phase II reaction includes anabolic or synthetic reactions. These reactions are also known as conjugation reactions. Example, glucuronidation, acetylation, methylation, sulfation and so on. In Phase I reaction, there is functionalization, that is, a functional group such as hydroxyl group or amino group is introduced into the drug molecule to impart polarity to the drug. Whereas in Phase II reaction, the Phase I metabolite is linked to the functional group donated by an endogenous molecule. This further enhances the polarity. The product of Phase II reaction is chemically reactive so that it can interact with a functional group donated by an endogenous molecule, and the final product is biologically inactive. As the reaction proceeds from Phase I to Phase II, the drug becomes more polar in nature. So the product formed in Phase I reaction is less polar compared to the product of Phase II reaction. Phase II reactions are fast compared to Phase I reactions which proceed slowly. Phase I reactions are catalyzed by microsomal enzymes, whereas Phase II reactions are catalyzed by non-microsomal enzymes except glucuronidation, which is catalyzed by microsomal enzymes. The enzymes are also known as transferases. For example, acetylation is catalyzed by acetyltransferase. Methylation is catalyzed by methyltransferases. So let's now move into the details of Phase II metabolism. So what happens in Phase II metabolism? A molecule endogenous to the body donates a portion of itself to the foreign molecule or the drug molecule, imparting polarity to the drug molecule and rendering it inactive. Phase II reactions include glucuronidation, sulfation, acetylation, methylation, glycine conjugation, and glutathione conjugation. Glucuronidation is catalyzed by a microsomal enzyme known as glucuronyl transferase enzyme. Here, there is donation of glucuronic acid from the endogenously synthesized UDP glucuronic acid to various substrates to form glucuronide conjugates so that these are eliminated through the kidney. Examples of such substrates are morphine, paracetamol, aspirin, diazepam, chloramphenicol and sulfonamides. So the next is sulfate conjugation. Here the enzyme is sulfotransferase. There is donation of sulfate groups from the endogenously synthesized molecule, that is PAPS, to various substrates to form sulfate conjugates so that they are excreted through the kidney. Examples of such substrates are acetaminophen, methyl dopa and corticosteroids. So the next is acetylation, which is catalyzed by the enzyme acetyltransferase, and the endogenous donor molecule is acetyl coenzyme A. Examples of substrates include isoniazid, dapsone, para-aminosalicylic acid and procainamide. Next is methylation. So here the cytosolic enzyme is methyltransferases and the endogenous donor molecule is S-adenosylmethionine. So the drug combines with S-adenosylmethionine to form methylated conjugates which are easily excreted through the kidney. Examples are 6-mercaptopurine is converted to 6-methyl-mercaptopurine. Another example is that of norepinephrine, which undergoes methylation to form epinephrine. Next is glycine conjugation. Here conjugation of substrate to glycine by enzyme glycine transferase takes place and the example is aspirin. In glutathione conjugation, conjugation of substrate to glutathione by enzyme glutathione transferase takes place and the example is ethacrynic acid. This brings us to the end of the topic. These are my references. Thanks for watching. Please like, subscribe and share.